Unit Operation Classroom. Today we are discussing heat exchanger area of a co-current double pipe heat exchanger. My name is Shekhar Bhattacharya. In a double pipe co-current heat exchanger, so this is a schematic diagram. Um, so shows almost like a heat exchanger, but basically this is a double pipe. So there'll be an annulus here. So here will be the one fluid and there will be another fluid. Normally this is the hot one. Okay. Operating at steady state, oil specific heat capacity is given and the flow rate is given at 100 degrees Celsius. So here oil is coming in here and is going like this, and water, cold water is also entering here and it's going like this, coming out. So this is basically a co-current flow. Okay. So oil, the flow rate is given and it enters at 100 degrees Celsius. Is being cooled, is being used to heat water. Again, it's flow rate and the specific heat capacity given here, entering at 20 degrees Celsius. So as it goes out and it's coming out at 50 degrees Celsius. That's what it says. And the overall heat transfer coefficient is given. We have to find out the area. We have to find out the area of the heat exchanger. This is a very simple problem. First, we calculate the total heat transfer rate. This is very standard, we know, and we can find out that is 441. So this watt, joule per watt, so this is so many kilowatts. We can calculate the outlet temperature of oil just by energy balance. Again, this is very standard, and which is 70 degrees Celsius. So this one will be coming out at 70 degrees Celsius. Okay. One interesting observation, the heat capacity rate is a new term, is defined as C dot, let's say M dot Cp, product of mass flow rate and the specific heat capacity. It represents the amount of heat required to raise the temperature of a flowing stream by 1 degree Celsius. So what is the heat capacity rate of oil? That is the flow rate multiplied specific heat capacity. So that's this one. And the heat capacity rate of water, it in fact it comes out the same. So therefore, the delta T for the two must be the same just from the energy balance. And as we see for the oil, this is 50 degrees Celsius and 20 degrees Celsius. That is 30 degrees Celsius here. In fact, for water, this is 50 degrees Celsius and 20 degrees Celsius. And for the oil, it's 100 degrees Celsius and 70 degrees Celsius. So for oil, it's 100 degrees Celsius and 70 degrees Celsius. Okay. So basically, this delta T it's being heated by 30 degrees Celsius. And since the specific heat capacity, since the heat capacity is the same, so this is coming at 50. So this is also 30 degrees Celsius. Okay, delta T. Since the heat capacity rate is the same for these two fluids, which is the product of mass flow rate and the specific capacity, product of mass flow rate and the specific capacity. This is just an observation. Of course, if we look at this temperature profile here, this is across the length of the heat exchanger. This is of course a tube side hot well. This is at 100 degrees Celsius to goes at 70 degrees Celsius. And the cold water is entering at 20 degrees Celsius from the same end. Remember, this is a co-current heat exchanger. And this is the another side, it's coming out at 50 degrees Celsius. We're showing this as a straight line, but in actual heat exchanger, this might not be the same because a lot of problems. Okay, it's not that simple. Anyway, uh, so this is 100 degrees Celsius, this is 70 degrees Celsius, and this is 20 degrees Celsius, and this is 50 degrees Celsius, and of course delta T is 30 degrees Celsius. Next, the delta T1 at the entry at this side is of course 100 minus 20, that's 80 degrees Celsius, and delta T2 is of course 20 degrees Celsius here. And we can easily calculate delta T dot mean, which is this one, and we know Q dot is equal to E delta T LM, and that is also very standard. So we can calculate the value of A. So that becomes 35 meters squared, assuming, of course, the electricity correction factor is equal to 1. And again, this is a schematic temperature profile. Okay? So the answer is 35 meters squared. Practical application of this problem. So in soap or detergent industry, hot molten fatty acids as present as stearic acid is cooled in a co-current heat exchanger. Why? Because if countercurrent heat exchanger is used, coldest cooling water meets the coldest fatty acid near the product outlet, leading to a local solidification or deposition of the tube wall, which basically means that uh, so the stearic acid, as a hot stearic acid comes in, and it gets, of course, it's cooled down, and if it's the counter current one, so this is the cold water coming in. So this basically tries to, since this is now cold, and this is the coldest water coming in, coldest way. So this tries to solidify the stearic acid, which leads to deposition and other problems. So if we use the co-current heat exchanger. So here what happens, this is the hot cherry acid coming in, it means the coldest food. So it's a high temperature gradient here. There's a very fast cooling. And as it cools, what happens, this stearic acid gets heated up. So gets cooled. So it gets cooled up, but this water is also getting heated up. So here the water is hot. So this does not lead to solidification or deposition of the water. Hmm. So in co-current heat exchanger, hot stearic acid and cold water entered from the same end, giving maximum delta T and rapid initial cooling. As both fatty acid and water move across the length of the heat exchanger, cooling water becomes warmer, thus avoiding solidification near the product outlet. So finally, the required heat transfer area is 35 meters square. So that's the answer.